Hi everyone, my name is John Dakin and I'm an applications engineer at QED Technologies. In this video, I'm going to talk about how our ASI stitching platform enables our customers to meet the demands of modern, high-precision optical manufacturing. It has become increasingly common to see optical surfaces specified with figure error requirements that surpass the accuracy of TE reference surfaces. In these situations, it becomes imperative to characterize and remove the instrument system error, or the reference wave error, from our measurements. I would like to walk through a quick example to illustrate just how efficiently and effectively the ASI can do just that. Behind me, we have the ASI stitching platform fitted with a QIS interferometer. Attached to the interferometer, we are using a Zygo 6-inch f2.2 transmission sphere. The manufacturer's stated system error of this reference surface is lambda over 10, or 63 nanometers peak to valley. The part we will be measuring for this example is a 2-inch diameter sphere with a concave radius of 77.2 millimeters. For this surface, the optical designers have specified a figure error tolerance of 5 nanometers RMS across a clear aperture of 34 millimeters. Let's get started with our measurements. We will begin by taking a single-shot measurement of the surface. This is the way that surfaces are commonly evaluated against specification using a simple benchtop interferometer. While using this method, the system error is included in the total output measurement, meaning that the resulting map is a combination of the error of the optic plus the error in the transmission sphere. Next, we will load our single-shot measurement into an analysis notebook to evaluate the overall error in the measurement against the specification. We can see that our basic measurement is failing the RMS figure error specification across the clear aperture. Again, it's important to keep in mind that the map we are evaluating includes the reference wave error as well as the figure error of the part under test. Next, we will demonstrate how to utilize the ASI's ability to characterize and subtract low-order reference wave error from the measurement. This will be accomplished by measuring the test piece in several orientations using what is known as a measurement lattice. During the acquisition process, the central subaperture will be measured 4 times, each separated by an A-axis rotation. A 5th off-axis measurement will also be taken. During the stitching process, the stitching algorithm is able to separate those features in each subaperture measurement that move along with the part and those that remain static across all subapertures. The low-order system errors are approximated using Zernike fitting and then subtracted from each subaperture prior to stitching. This entire process is done automatically and typically only takes a few seconds. By clicking into the Output Maps notebook page, we can inspect the calculated reference wave error of the metrology system. QED.net software also gives us the flexibility to modify the way in which the low-order error is fit, using more or fewer Zernike terms as is suitable for your specific process. I will discuss this topic a bit further later on in the video. We will now load our stitched measurement into the analysis notebook and evaluate the figure error across the clear aperture. Now that the low-order system error has been removed from the measurement, we can see that our example test piece actually conforms to the specification. This corrected map provides a more accurate representation of the part as it isolates and quantifies only the true figure error. In other words, the part was within specification all along. The stitching process simply enabled us to separate the absolute figure error in the part from the systematic error from the instrument. If we compare our two measurements, the basic measurement on the left and the stitched measurement on the right, we can see that they are substantially different. Because the stitched measurement has removed the reference wave error, if we were to subtract the stitched measurement from the basic measurement map, we will be left with an approximation of the system error. We can view the difference map alongside the calculated reference wave error map. If we apply the same z-scaling to the two maps, we can clearly see how closely they match. Previously, I had mentioned that QED.net gives us the flexibility to modify the method in which the reference wave error is calculated. We can independently select the number of radial and azimuthal orders used in the calculation. By default, 6 radial and 6 azimuthal orders are used. However, in some cases, such as this example with our 6-inch f2.2, where the transmission sphere exhibits enough high-order error to justify increasing the number of orders used in the reference wave calculation. This consideration should be monitored by inspecting the stitching mismatch map, looking for the outline of subapertures or for repeating structure in the mismatch map. By doing this, we can model the reference wave error more accurately and in turn improve the overall stitched measurement accuracy. In this figure, we can see how increasing the number of orders from 6 to 10 to 14 orders provides a more accurate model of the higher frequency system errors. In some cases, it may be beneficial to further characterize the mid-spatial frequency errors in the reference wave. This can be done using a calibration process known as random average reference, which will be the subject of a separate video. Thank you for watching our demonstration on how the ASI characterizes and removes system error from stitched measurements. Please do not hesitate to reach out to the Applications Engineering Group if you would like to learn more about how ASI stitching can improve your precision optics manufacturing processes.